Denko Fasoka ninyi horonya ye Niminku mimanya Okamu sinanya
Skeletal muscles, like the biceps brachii, attach to bone via connective tissue called tendons. Muscles are composed of bundles of muscle fibers. Each bundle is separated by connective tissues known as perimysium. Each fasciculus is made up of muscle fibers, which are separated by connective tissue called endomysium. Skeletal muscle fibers or cells are multinucleated and striated in appearance. Muscle cells are composed of subunits called myofibrils. Each myofibril is made up of several myofilaments. The two types of myofilament shown in red are composed primarily of the protein myosin and a thin myofilament shown in blue composed mainly of the protein actin. The repeating arrangement of thick and thin myofilaments serves as the fundamental subunit of striated muscle contraction. These subunits are called sarcomeres. A sarcomere contraction is represented by the shortening of the distance between the Z-lines. The sarcomere shortens because the thin filaments slide past the thick filaments. In 3D, each thick myofilament is surrounded by 6 thin myofilaments arranged in a hexagonal pattern. The 3D arrangement of sliding myofilaments is the microscopic basis of muscle contraction.
At the start of the contraction, stored calcium ions are released into the cytoplasm. Calcium ions expose binding sites on the actin molecules. Globular heads on the myosin can bind to these sites, forming cross bridges. Repeated binding and release moves the filaments relative to one another, and as this occurs simultaneously in many sarcomeres, the entire muscle shortens or contracts. This process requires energy in the form of ATP.
With calcium elevated around the myofibrils, myosin binding sites on actin are exposed, allowing interaction of the myosin cross bridges with actin. Release of the myosin cross bridge from actin requires binding of ATP. After ATP binds, it is split to ADP and inorganic phosphate. The energy derived from this reaction is utilized to caulk the cross bridge in preparation for the power stroke. The power stroke is initiated when the myosin cross bridge binds to actin. The cycle begins anew when another ATP binds to myosin. At rest, most cross bridges are in the caulked configuration, prepared to interact with actin.
Acetylcholine binds to receptors on muscle fibers. These receptors open the sodium-gated channels, causing sodium to rush in and potassium ions to trickle out. Because the channels are more permeable to sodium, the muscle fibers become positively charged, making an action potential. The action potential spreads through the muscle fiber network of T tubules, depolarizing the inner portion of the muscle fiber. The depolarization activates calcium channels in the T tubule membrane. Calcium channels are activated, causing the sarcoplasmic reticulum to release calcium ions. The calcium binds to actin-containing thin filaments. Calcium ion is used to unblock the binding sites blocked by troponin. Myosin binds to the uncovered binding sites on the thin filament. Myosin is afterwards bound to actin in the strong binding state. ATP binds myosin molecules together, allowing it to release actin and be in a weak binding state. Myosin hydrolyzes ATP and uses the energy to move. The steps from myosin binding to the uncovered binding sites repeats and repeats as long as ATP is available and calcium is present on the thin filaments. While these are happening, calcium ions are actively pumped back into the sarcoplasmic reticulum. When ATP is consumed, myosin stops binding with the thin filament and the contraction stops.
Tula